Okay, guess we'll get started. So are things proceeding well for everyone with your final projects? You're all more or less keeping up with the benchmarks you set? Okay, if there are any issues, please let me know. Any questions at this point about the final homework assignment? Just remember, everyone, we don't have class a week from today, so next Tuesday is the final homework assignments due date. So just make sure you're keeping up with that. I'll give back your homework 5s and solutions to those at the end of class, but I guess for now we can pick up where we left off, and what we'll be covering today is the final one of our case study lectures, where we try to look at a real-world problem area in which people use some of the techniques we've been covering the rest of the class. Well, specifically we're looking at a case study of genetic regulatory networks. I think this is kind of an interesting and important problem area that has seen a lot of interest in biological contexts and really the past 10 years or so, but uses a lot of the sort of model inference techniques we've been looking at in the last part of this class. So I hope we can use it as kind of a review of some of the techniques we've seen and how they could apply to a particular real-world problem area. But basically what we're interested in here is the problem primarily of transcriptional regulation, although the same principles would apply to other sorts of regulation. But basically what we would assume is that we've got some genome, and that genome will contain sets of genes. So this might represent the transcribed region or a particular gene, and those would often code for proteins. So we go from gene to protein. And these genes often have regulation at various levels, one of them being transcriptional regulation, in which proteins may come in from other genes and regulate when this particular gene is active. And likewise, the proteins produced by this gene may be regulators for other genes. And if that's the case, then we would say that this gene is a transcription factor. And basically what we're going to be interested in today is trying to study the problem of how you would figure out patterns of regulation among these transcription factors. And in a real biological system, these can be quite complicated. You might have some external stimulus that eventually triggers a few early transcription factors, and maybe those go on to trigger various late transcription factors in different ways, make some of them more active, make some of them less active, eventually triggering many downstream genes, some of which might be activated by the external signal, some of them suppressed, through complicated patterns of regulation. And figuring out what these patterns are from biological data of different kinds tends to be a pretty difficult problem. And we're going to see how some of the methods we've looked at in this class apply to that problem. Now, there are a lot of different kinds of data you can use. So there are some kinds of experimental data that would give us, for example, information specifically about whether a transcription factor is binding to a particular region in the promoter of a gene. So there are experimental assays we can get that would tell us that this particular protein is bound to this particular sequence of the promoter of another protein. That is one kind of data we could use to resolve this. Sometimes you can make predictions about these transcription factors and where they bind just based on the sequence. So there are ways to use some of the methods we've seen to figure out what the binding sites of these transcription factors are, learning those from examples. We actually briefly saw how you would do that. Does anyone remember how we could learn the pattern of a binding site for a transcription factor. Yeah, so you could create a Gibbs sampler. Basically, you would take lots of examples, try to figure out in pieces of sequence that you know contain the binding site, try to sample over possible places that binding site might be occurring, and then learn a model that would tell you how likely that binding site is to be in any one place versus another place. But what I want to focus on today is primarily a particular kind of data, which by itself is not necessarily the only thing you would want to use, but tends to be very good data for this kind of problem, and that is gene expression data. Right, so gene expression data is basically just literally telling us how active a particular gene is. So how many transcripts are being produced by this gene, which is usually treated as at least approximately proportional to the amount of protein that's present. And what we would often want to be able to do is look at expression of many different genes, see how active they are in different conditions, and based on that, try to figure out which genes are turning on and off at the same time, and they therefore may be involved in regulatory relationships. So in the text, you may get an idea that some aspects of the text are kind of dated at this point. I talk about this mostly in terms of microarray expression. So microarray is one technology for measuring these. Today, that would more often be RNA sequencing that you would use. But for the purposes of what we're talking about today, you can almost think of those interchangeably. Basically, we'll think that we have some way of measuring activity levels of different genes, and we're going to try to use that as our data to figure out the patterns of activity, so how these might be joined together in some kind of regulatory network. So are there any questions about any of that before we move on to the more computational material? And how many of you are familiar with, well, I guess what gene expression is? Okay. All right, so in terms of what we're going to be trying to do with this, as usual, we're going to need to think about some modeling and abstraction. And the main abstraction I'm going to be using here is to assume that we have this expression data, and we'll assume it comes in the form of a matrix that I'll call A, where A will have elements A11, A12, up through A1N, let's say, and through AM1 and AMN. So we've got an M by N matrix. And what we'll assume here is that the M here refers to genes, and the N here refers to conditions. So the idea would be that we're monitoring a certain number M of genes, and we're monitoring a certain number N of conditions, and then in each condition we'll profile the activity of all M genes. Now, both of those are kind of approximations to a degree. So when I say genes here in practice, that might literally be one measurement per gene. Very often it would be something a little more nuanced than that. So we might have measurements of different transcripts or different exons. Today you can even do that at a single base resolution. So how active is each base in the gene? How often is it showing up in transcripts? But basically we can assume we've got something that roughly is profiling the genes. And conditions can refer to a lot of different things. So it may literally be different conditions under which we run an experiment. So maybe we're measuring expression of yeast, and we want to see if you feed them different nutrients, how does that change the expression? So we'll be looking at different conditions corresponding to the different nutrients. It may be different patients, so we're sampling, let's say, diseased livers from 100 different patients with cirrhosis of the liver, let's say. We want to know how expression is changing among them. So it could be almost anything here, but there are some important things we need to know about M and N that will constrain the kinds of solutions we can consider. And the most important thing is that the number of genes, M, is typically going to be the order of 10,000 to 100,000. Could be larger, could be smaller, but usually for this kind of problem, we'll be thinking of the number of genes we're looking at in that general range. The number of conditions is going to be, depending on the sort of condition we're considering, maybe the order of 10 to 100. So usually you're not going to be looking at tens of thousands of patients or running tens of thousands of experiments. That's changing too, so now that many things are becoming more automated than they used to be, maybe we can start to think about that. But in general, M is going to be a lot larger than N, and that's kind of an important thing to remember for thinking about how we'll go about solving these problems. So does that make sense to everyone? All right, so what we're trying to do here in general, at least in our end goal, our ideal goal, if we could really solve everything we want to solve, is put together one of these regulatory networks describing the activities of these genes. So we've got M genes, and we can think of those as gene 1, gene 2, gene 3, gene 4, and so on. And we're trying to figure out, in the ideal case, that maybe gene 1 regulates genes 2 and 3, and gene 2 regulates gene 3 as well, and gene 3 regulates gene 4. So in the ideal case, we would like to figure out exactly that. Even for this representation, there's a fair amount of nuance involved in it. So there are versions of this where we might be interested in directed or undirected graphs. So what might it mean to have a directed graph representation here versus an undirected? What difference would it make? What would be the biological interpretation of a directed edge, let's say?
That gene 1 regulates gene 2 in some fashion.
Yeah, so a directed edge would be more meaningful in a sense, more biologically meaningful, because of course it means something different for transcription factor 1 to bind to gene 2 versus transcription factor 2 binding to gene 1. Often we'll end up with a model that is unidirectional because, or basically undirected, because as we'll see, it's hard to find these kinds of graphs. And typically, you need some extra hint or extra information if you're going to find directions. We can also consider weighted or unweighted versions of these graphs. What might an interpretation of a weighted version of one of these graphs be? What might it mean to assign a weight to this edge? It could correspond to a strength of interaction, so it may be that gene 1 has a very strong influence on the expression level of gene 3 and gene 2 a weak one, so we might want to give a high weight here versus a low weight here. We may care about the sign of the interaction, so maybe gene 1 is a positive regulator of gene 3, so when 1 goes up, 3 goes up, whereas gene 2 might be a negative regulator, so when 2 goes up, 3 goes down. It could have other interpretations. It might be a confidence in the interaction. So if we're not completely sure which edges are there, we might assign a 90% confidence to this one if we're pretty sure it's there, and 50 to this one if we're not so sure, and so forth. But basically, there are a lot of ways of thinking about this. But in some sense, what we're going to assume is that we're trying to find a graph G equals VE, where V is going to be given to us, so that's our set of genes, one node per gene, and E is really the thing we're trying to find, and may or may not have a weight function associated with it. And that's going to create some problems for us. So the way I've described this problem, you should immediately see that there are going to be some challenges we need to deal with. What's the big issue here? What would be the hardest thing about solving this in a sense? Maybe another way to put it is, I'll suggest that this is an impossible problem. We can't possibly solve this. Why might you think that? Well, the main issue here is that our space of models is much bigger than the amount of data we have. You can't really hope to train a model if you're trying to learn many more parameters than you have data points. Our data points here are order of mn, so we've got about m times n data points. Our model basically consists of E, or essentially we'd have one variable for each edge that might be an E, and how big is that? So that would be n choose 2, or actually m choose 2. So So if we've got m genes, we would have m choose 2 possible edges. And if m is much bigger than n, then m choose 2 is going to be much bigger than mn. So this is, on the surface, a hard or almost impossible problem. We can't possibly learn which model from our universe of models is correct from the data we have. So that raises one of the immediate issues we often need to worry about in model inference, and that is we kind of have to match our model to the data we have available for us. So there are different ways people deal with that, and one way is to try to scale back what it is you're trying to do and maybe say that we're not going to be able to learn from the universe of all possible graphs here, so we'll try to consider a more restricted set of graphs where maybe we have some hope of learning the possible model. And one way that's commonly done is to convert this to the simpler problem of clustering. So basically trying to figure out, instead of from the set of all possible graphs, what is the right graph, learn from a restricted set of graphs, where in a sense what we're trying to figure out is that there are groups of genes that are under common regulation, and we don't really care how these genes are regulating one another. We just care that when something happens to one of these genes, it causes something to happen to all of these others, and that might be independent of a different group of genes. We can think of this as a version of this network learning problem where we're considering a much more restricted class of networks. In particular, where we might think of this as considering a class of networks where the only graphs we're allowed to have are graphs where every node is part of a clique. So in a sense, the graph is a union of cliques of subsets of the nodes. Does anyone remember what a clique is? Yeah, fully connected subgraph. So if we're thinking about this as a clustering problem, we might say that in a sense what we're trying to do is learn from a simpler universe of possible models, and then there are a lot of different techniques we've seen that you can apply to that kind of problem. Often the first thing we need to worry about in a clustering problem is simply how we would figure out if two genes are behaving similarly. So in some sense, what we're trying to do is put together genes in common cliques if they behave similarly. So we need a way of quantifying what it means to behave similarly given our input data. So there are some simple standard ways to do that. So you can use, for example, Euclidean distance. So in the Euclidean distance, what we would say is that the distance between genes I and j, so let's call that d of, say, dij, we would say is square root of sum of squares of aij, aik minus ajk squared, summed over all of our possible conditions k. That would give us one way of saying how far apart are two different genes in terms of their patterns of expression. So what kind of distance would you be looking for to suggest the two genes should be in the same clique? In general, you look for a small distance. So if two genes have a very similar pattern of expression, then you'd expect this distance to be small, so it's more likely they would be in the same clique versus far apart. There are other measures from statistics. For example, you'll often see the correlation coefficient used as a measure of distance for these kinds of problems. That can be a little better because it will capture cases where genes vary in opposite directions. So in general, if gene 1 always goes down and gene 2 goes up, we would say probably those are under common regulation, but they would have large Euclidean distance with small correlation coefficient. So that would be defined as the covariance of the vectors corresponding to those two genes, divided by the square roots of their variances. So that would be another way we can quantify this. Often in these kinds of problems, we'll see distances that are more easily interpretable, and good measures come from the idea of information theory, which is usually about measuring, in some sense, entropy or information content of a signal. And for these kinds of measures, we can think of these coming from our data by talking about how much information is contained in a gene or a pair of genes, and how much information is contained in the signals looking at the patterns of expressions across genes. Most of this is based on simple entropy formula, which is that we're pretty much taking the sum of Pij log Pij, I guess you should put a negative in front of it, where Pij would be the probability of seeing a particular expression value in condition of gene I in condition J versus times the log probability of that. It's just a basic formula from information theory that tells you how many bits of information are contained in a signal. And that's something we can often apply to a data set like this in a few different ways. So one of the ways you'll commonly see that is to try discretizing your data set. And that gives you a way of talking about information content of streams of data in the data set. So for example, if we've got a set of continuous values here, usually what would be coming out of our expression data, we can try turning them into, let's say, pluses and minuses to tell us which genes are we saying have high expression or low expression under any given condition. And then given a vector of these pluses and minuses, so for example, minus, plus, minus, minus, you can assign an information content to that vector using the entropy formula. So we could say that something like this stream, if this were, say, the expression of gene i's, that would be corresponding to row I of our data set. That would be given by minus the fraction of things that have a minus. That would be 3/4 log 3/4 plus the fraction that have a plus, 1/4 log 1/4. That would give us a measure of information content of that gene. And we could do the same thing for some other gene, J. And then we could do the same thing for pairs of genes. So we could talk about if maybe this one was plus, plus, minus, minus, we could come up with an entropy of that signal. And we could come up with an entropy of the paired signal, I and J, which would then have characters minus, plus, 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 minus, 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 minus. We can talk about what fraction of the signals are minus plus, what fraction are plus plus, what fraction are minus minus, and come up with an entropy for that. And that would generally be combined into a formula that we know of as the mutual information, which is basically encoded as the entropy of A plus the entropy of J, or the entropy of I plus the entropy of J minus the joint entropy of I and J. It's another way of quantifying whether these signals are different from one another. If you have the same signal, then the entropy of I, which we'll call H of AI, and the entropy of J will be about the same, and the entropy of I and J, the joint entropy, will be about the same as the sum of those. You get a signal that's around 0. If they're independent of one another, then, or excuse me, if they're the same as one another, this will be the same as either of these. If they're independent, this will be the same as the sum of these. So independent, you will end up with about a 0 signal. If they are the same, you'll end up with a signal that's about equal to the amount of information in one of them. Just another way of quantifying these things. All right, so any question about any of this so far? All right, so these are basically just different ways of measuring distances. But the real point here is that we're trying to get to how we would use this to do clustering. So we want to find one of these union of Cleek graphs. Now, one way we could pose this is to say we have taken our input data, we use whatever measure we want to use. Let's say we want to use mutual information. And let's say with the mutual information, we would like a graph that has basically a lot of edges indicating that we've got very similar genes, so very similar patterns of expression. So we want a high amount of mutual information. And suppose I declare that what we're going to do is take our original graph and try to break it into K clusters so that we maximize the mutual information summed over all the pairs of genes in those clusters. How would we do that? Well, what computational problem am I describing? So we've got a graph. We can pretty easily compute these mutual informations, so we can assign weights to all the edges of the graph. And what we're trying to do is break that graph into K subsets, maximizing the sum of all of the pairwise edges within each subset, or equivalently minimizing the edges that go between the subsets. Well, if you remember all the way back to, I guess this would be the second week of class, this is an example of a cut problem. So depending on exactly what measure we use and how we phrase it, you might get different cut problems. But typically, a clustering problem would be posed as some version of a max K-cut problem. And why is that important? What do we know about max K-cut problems? The main thing that's important about them is they're intractable. This is an NP-hard problem, and that's going to tell us something about how we would want to go about solving this. We're not going to be able to come up with a good, efficient algorithm, so we have to consider alternatives. And usually the alternatives people would look at for this kind of problem is to do some kind of heuristic. So of course you could do an approximation algorithm, you could do a branch and bound, but usually people use heuristics for this kind of thing. So there are some simple heuristics that date to kind of the early days of these gene expression studies. So one of them was something called the guilt by association heuristic. And the basic idea behind this one is that we'll set some kind of cutoff, so let's say some threshold mutual information we care about, and we'll take one gene and we'll ask what are all the neighbors that are close enough by that cutoff. And then we'll consider the neighbors of those. Maybe they're sometimes each other's neighbors. Maybe they're sometimes adding distinct neighbors. And you just keep doing that until you end up with what's called the transitive closure of this neighbor operation. Basically, you just keep adding neighbors until every new neighbor you try to add is in that set already. And then you just say, we'll call this a clique, add all the other missing edges. That's a clique. And then we pick a node we haven't worked with yet and start over again until we've ended up assigning every node to a clique. So this is really not a great clustering heuristic. You could probably show that this can be pretty far from optimal for these K-cut versions of this problem, but it's a simple thing that people could do even in the early days of gene expression studies. That's one way this was often handled. So any questions about that yet? Another way this is often done is hierarchical clustering. So in the hierarchical clustering, it's another heuristic where basically what we would do is take all of our nodes, take our graph of the weights, the distances we've computed between these, and basically just start pulling together nodes that are more similar to one another. So maybe you pick the two closest nodes, whatever those are, and then you can kind of say that these become an initial cluster. And there are different ways of posing this, but a typical one would be to say, then you try to estimate the center of the cluster, and then you see what's closest among all the remaining nodes and that center. Maybe these two are the next closest, so you find a center for them. And maybe it happens that these centers are the next closest thing, so you group them together. And basically, you just keep doing this until you get to some threshold where you're connecting things that are too far apart and you no longer want to continue. And at that point, you can say you've got a set of clusters. It's another heuristic people often use for these problems. So, any questions about that? All right, so I think we can do somewhat better than this. So there are certainly better, or at least more theoretically sound ways of doing clustering. And I want to work through one way of doing this using some of the tools we've seen recently, and that is to think of clustering as a kind of expectation maximization problem. So if we want to use EM to do clustering, then generally what we're going to want to do is think about this in terms of probabilities. So think about likelihoods of clusters with respect to our data. And to do that, we need to be a bit more explicit about what we're trying to do with the data and how we're planning to use it. So we would typically begin by formalizing our input. We can more or less say these vectors of the A's are our input. But put this in the language we've typically seen for EM, I'll just rephrase those as X's. So Xi now will be our vector of inputs because we've been using X to refer to the data available to our problem. So X we'll just say is the same as AI. And we would want to have an output, so a model we're trying to infer lambda. And this model lambda is going to be, in some sense, a representation of our clustering assignments. And it turns out that a convenient way of doing that is to think of your data as a set of kind of clouds of points corresponding to your clusters. And then what we're going to declare as our model is a cluster center or cluster representative for each of these clusters. So kind of an average point that represents the cluster. And in terms of that, we'll be able to pose a probability model of basically how likely is it that we see all of these X points given the cluster centers. So we'll declare this lambda to consist of a set of these cluster centers, and they'll look a lot like our input vectors. So we'll have a C1 vector, which will be C11, C12, which is C1n, and that will correspond to the expression level of cluster center 1 and gene 1, gene 2, and so forth, up to gene n, and then we'll have some set of k of these cluster centers. CK1, CK2, through CKn. And that would give us the model we're trying to infer. So we're trying to find a set of these k cluster centers to correspond to our input data set, which is the X's, which is really just the same as the A vectors we've been talking about. Now, before we get to how we would do this by EM, it's worth considering what model are we trying to solve for the EM problem. So what is the likelihood that we're trying to optimize? Because EM would usually be something we use to maximize the likelihood. And the way we're going to do that is to propose a particular model for generating the data from the cluster centers. And that model is going to say that if a point xi is generated from a cluster center, let's call it Cj, then our assumption is going to be that xi is equal to Cj plus a vector of normal noise terms. So let's just say mean 0, variance 1 in each dimension. So in other words, if we have a cluster center with value C11 for its expression level of gene 1, then we would say all the points in that cluster center should be drawn from a probability distribution where their expression level in gene 1 is C11 plus a normal 0, 1 random variable, or equivalently a normal C11, 1 normal random variable. So does that make sense to everyone? So basically you can kind of think of this, that the cluster centers we're saying are the average behavior of the genes in a cluster, and then each gene, we're assuming, is drawn from a normal distribution in each dimension around that center. And that model gives us a way of specifying a likelihood function for our data. So in particular, we can say the probability of a complete data set, given our set of cluster centers, would be what we would get by taking the products of the probabilities of generating each of the dimensions of each of the observed data points, given this model of where they're drawn from. So in other words, we could say we're taking the product I equals 1 to n over our data points, and then for each of those, we would take a sum over the possible cluster centers of the probability that vector xj, vector xi, given that, well, the probability of, let's call it the observed value here, x given that the cluster, which we will call C of XL, is equal to the jth cluster, excuse me, C sub j. So in other words, basically what we're doing is just what I was saying here. What we'll do is take a product over all of our data points, a sum over all of the possible cluster assignments at that data point, of the probability of generating that data point from that cluster assignment. And we can also throw in that maybe there is a prior probability on the cluster assignments, so some prior probability that the cluster of that particular assignment is equal to the cluster center we're considering. So in other words, basically what we're doing is just saying that there is a large number of data points we're generating, so each of our genes and each of our conditions, and then each one we can think of as a normal random variable drawn from this complicated distribution. And by assuming they're all independent, we can just take a product over each of those data points to get an overall likelihood function. And since we're assuming normal random variables, we can basically simplify that to a product over a sum over a product of each of these normal terms, 1 over square root of 2 pi, e to the minus xim minus, excuse me, xil minus cjl squared over 2. Basically just a product of lots of these normal terms measuring the difference between the observed value and the cluster center in each dimension we're considering. So does that make sense to everyone? Okay, so that basically is the problem we're trying to solve here. And what we would like to do is solve this by expectation maximization. And to do that, what do we need? What do we have to come up with to specify an EM algorithm? Well, we need to propose some latent variables. So we're going to want to propose something that we don't know about our problem that would make the problem easy to solve in a sense. So what might be something we could use as a latent variable for this problem? What we're assuming is we're trying to infer the cluster centers given the data. So what would make it easy to infer cluster centers? Well, a good choice of latent variables for this problem is the assignment of the data points to the cluster centers. So if we knew which of the input data points came from each cluster center, then we could pretty easily figure out what the cluster centers should look like for the data points assigned to them. And we can also relatively easily go in the opposite direction. So once we've figured out what the cluster centers look like, we can figure out how plausible it is that any given data point came from any given cluster center. That would give us a way of solving our problem. So basically what we're going to do is propose our latent variables our y's are going to be the assignments of the observed data points to the cluster centers. And we can abbreviate those by saying that there's some indicator variable I sub ij, where I sub ij will be 1, let's say, if data point I comes from cluster center j and 0 otherwise. Now in practice, what we're really going to want is to work with the expectations of these. So I'll just abbreviate that the expectation of iij is going to be, call it P sub ij. Basically, it corresponds to the probability that data point I comes from cluster j. All right, so if we knew for certain which data points came from which cluster, how could we figure out what the cluster centers should look like? Because that, in a sense, is what we're trying to do in the M step of our algorithm. We're trying to figure out what the cluster centers look like. So suppose we knew for certain exactly which data points, which of these capital I sub little ij's were 1 and which were 0. How could we figure out the cluster centers? So let's say figure out C sub jl, where the Well, for these kinds of Gaussian models, it's sort of the obvious thing if you knew exactly which genes were in which cluster centers. What you would want to do is take the sum over the assignments of every gene I in position L, and just divide that by the number of genes in the cluster. So let's maybe call that n sub j, and we can call this, I don't know, let's call it x, superscript j here, to mean the set of genes that are in cluster center j. And then what we're doing is just the obvious thing. For each gene, or for each of the genes, average over all of the points you observe in the cluster. That's your maximum likelihood estimate of the center of that cluster, so the average gene expression value for that cluster. Does that make sense to everyone? And basically, just graphically, what we're saying is, if we've got a set of data points, and we're declaring that these are a cluster, then take the average of all of these, and the cluster center is the average of them. Now, it gets a little trickier if we are working with these latent variables, because in an EM algorithm, you don't necessarily assume you know the latent variables. You would assume you know the distribution over them, or in this case, we can get away with knowing the expectation of them. So if you knew the expected values of the cluster assignments, then you can do almost the same thing. Basically, you just take a weighted average over the probability of any given assignment. So in other words, you would say that the cluster center J in position L would get a value that's equal to the expected number of points assigned to it. So 1 over, say, Pij. So Pij would then be the expected number of points assigned to cluster J, and then we would multiply that by the sum over all of our data points of xil Pij. So in other words, you're just taking a weighted average where you're putting more weight on points that have a high probability of being in the cluster, less weight on points with a low probability of being in the cluster. Right, so does that make sense to everyone? So in terms of this graphical representation, what that might mean is if we think there's a very high probability these points are assigned to this cluster, but a very low probability these points are assigned to it, then maybe the cluster center would get pulled just a little bit in the direction of these points, because we're weighting them, but we're not weighting them very much, since we think they're probably not in that cluster. Does that make sense to everyone? Okay, so that is the M step. And the other thing we're going to need is an E step. So what are we trying to do in the E step? What do we want to figure out in the E step of this algorithm?
Which points to assign to the, which data points to assign to the clusters?
Yeah. So if we were doing a full EM algorithm, we want to know the probability distributions over these assignment variables. But as I said, we can get away with knowing the expected values of those. And in this case, it's not quite obvious that you can do this from this expression, because this actually isn't linear in the PIJs, but you can play with the math and it works out. But basically what we're going to want to do is get the expected values of these I variables, and the way we can do that is by saying, how likely is it that any particular observed data point came from any particular cluster? So we'd like to know the probability that, let's say, vector xi's or ith data point has the set of values it has, given that it came from a cluster is C of xi is Cj, or equivalently, given that I sub ij equals 1. So what is the probability of observing the values you observe given that particular assignment? And we can, with a little application of conditional probability, say that that is equivalent to the probability that, let's say, this cluster center C of xi Pij, or Pij equals 1, given xi, and then this would be multiplied by probability, well here, let's say probability C of xi equals 1, or equals Cj, divided by probability of xi. So in other words, if we want to figure out the probability of the cluster assignment, we can say that that is proportional to the probability of the data given the cluster assignment. So that's just normal conditional probability. And most of these things we can kind of factor out. We don't really care what this is. It's just a scaling factor. So that's something you can kind of average out. We could assign prior probabilities to different clusters, but usually we'll just say that prior probability is 1 for any given cluster. So more or less we can treat these things independently, and that lets us pretty much say that the probability of a point being assigned to a cluster is equivalent to the probability of the data for that point being generated from the cluster, normalized by some z factor we would estimate, which is equivalent to saying that we can estimate Pij by asking for the product over all of the genes of 1 over square root of 2 pi, e to the minus xil minus cjl squared over 2. So just the probability over all genes L that our particular, or all conditions L that our gene I would give us the particular value of that cluster center, divided by the sum of this over all of the cluster centers. So particular sum over the product, 1 over square root of 2 pi, e to the minus xi L minus c j prime L squared over 2, or summing here over j prime, and then taking the product over all here and here. So in other words, basically what we're just saying is, if you look at a particular data point here, we look at what is the probability of generating its first expression value from this particular cluster center according to the Gaussian distribution times the probability according to the Gaussian generating its second value, its third value, and so forth. All of that gives us a relative likelihood for this point being generated by this cluster center, and then we repeat that for this cluster center and for whatever other cluster centers we have. We get effectively a set of posterior weights of that point coming from any of those cluster centers, and then the ratios of those weights gives us our Pij values. Does that make sense to everyone? Right, so if we put those together, we pretty much end up with an EM algorithm. You just need to come up with some way of initializing, and often you can initialize by kind of randomly assigning points to clusters, and then just start iterating. So once you've got a random assignment of points to clusters, you can get your cluster centers by an M step, you can reassign the points by an E step, and then just go back and forth, and should converge in a few steps. So does that make sense to everyone? Right, so this is, I think it's a good clustering method. It's one that you don't see as often as some of the more popular heuristic ones. It's very similar to what's probably the most popular heuristic clustering method. So many of you may have seen what's called k-means clustering. This EM algorithm is very similar to k-means. The only real difference is in k-means clustering, instead of finding these Pijs, you would find the vector and then just declare the cluster with highest likelihood. The indicator variable becomes 1, all the others become 0. So basically you just say, instead of fractionally assigning points to clusters, you assign the point completely to its one best cluster. Then you get k-means clustering. But the EM version is a little sounder probabilistically, so it's actually a slightly better way of doing this. Right, so any questions about any of that? All right, so all of that is basically meant to illustrate that there are some ways we can bring together some of the methods we've seen before to solve a simpler version of this problem of finding these network models. but often we really want to go about finding the full network. And so what I'm going to do is move on to a more holistic version of the model, where maybe we're going to say we've got our genes, say, A1, A2, A3, A4, and we really want to figure out not just that these are in a co-expression network, but that gene 2 is regulated by gene 1, and gene 3 is regulated by gene 1, and gene 4 is regulated by genes 1 and 2. So if we want to figure out things from the full network model, then we're going to need to come up with some ways of dealing with the problem that we don't really have enough data to solve the full problem we're trying to solve. We have actually seen some other ways you can get around that problem, although it may not be obvious that they solve this. So can anyone think of how else we might deal with this issue? The fact that there are simply too many models to choose from? Well, in practice, what people would often do is to say that maybe there are lots of models that might be consistent with the data, but we're going to try to put some bias into it so we can find good models. And very often the way we'll see for doing that is throwing some prior on top of the set of models we have to bias it so that we're picking models consistent with the data, but biased towards a set we think are particularly good. One version of that we saw in the last class that we very often use is an anti-complexity prior. So we'll bias it to consider simpler models of the data if we're considering between similar quality models that are all about similar in terms of how well they represent the data. We would bias it to pick among the simpler among those. We may also throw in prior knowledge that suggests there should be or should not be particular edges in the model. That can give us a way of kind of working with less data using our prior estimates to kind of fill in the pieces where we don't have good data to decide between them. But all of that comes down to is that we want to have some way of posing a representation of how well the model represents the data, and then we can bring in these other things that will bias it to pick models that are simple and that are consistent with our prior expectations. And all of that eventually comes down to the question of trying to find some likelihood function to represent the likelihood of a particular network given a particular data set. So typically this would be the likelihood of our expression data, the matrix A, given some model. And very often what this model will come down to is the graph G equals V E we were talking about before, but now allowing this to float on the universe of all possible graphs for our particular model. And this will usually come down to trying to find some way of saying what the likelihood of a data set is given a particular graph. So there's a class of model that's often used for this sort of problem, where we've got a lot of independent measures of data, and we're trying to figure out how those are related to one another. And those are often phrased in terms of what's called a Bayesian graphical model. There are a few other equivalent terms for these, but basically what they are is a way of trying to figure out relationships among a large data set and learn a model that would give us a way of concisely representing which pieces of data are related to one another and how. And in a Bayesian graphical version of this kind of model, what we're trying to do is learn a graph that will tell us a likelihood function for the expression vectors corresponding to these genes. And in particular, what the Bayesian graphical model would assume is that the likelihood function we're trying to find can be expressed as a product over all of our conditions, so product over, let's say, conditions J, of a probability of each of these individual genes, assuming the graph is telling us what those values might depend on. So in other words, saying that we would have a product of gene 1 taking on values A1j over all of our conditions j. And we're assuming for this particular graph that that depends on nothing else. It's just a stream of information that we'll assign the likelihood to, times a product times a probability of generating the values we observe for gene 2, let's say A2j, given that we are assuming those depend on the values of gene 1 in the same conditions, so A1j, times the probabilities of, let's say, A3j, given that these depend on the values of gene 1 in the same condition, times a product of the probability of A4j, given that that depends on the values of both gene 1 and gene 2 in the same conditions. And that's basically the assumption of the Bayesian graphical model, that each of the variables we're observing depends on a limited subset of other variables, and that dependence is encoded in the graph we're trying to learn. Now, it may be that you can have indirect effects. So if we didn't have this edge here, it might be that gene 2 depends on gene 1, and gene 4 depends on gene 2. But then we would say that gene 4 depends on gene 1 only transitively through gene 2. So the model is basically restricting the set of things we consider in assigning our likelihood function. Now, it probably isn't so clear yet how that would be helpful, but I think once we get into how you would actually figure out the value of this likelihood for a real data set, it'll be a lot clearer why this is a useful thing to do. But let me just pause for a moment here. Are there any questions yet about this, what we're trying to do here? Okay, well, let's suppose that we have a data set here. So suppose we've got 4 different genes and 4 different conditions. Let's call it C1, C2, C3, C4. We'll just imagine that we've measured various expression values. So maybe 0.9, 0.8, 0.6, 0.5, 0.1, 0.2, 0.4, 0.3, and so on, just making up a few different values of expression of these different genes in these different conditions. So what we would like to be able to do is take a data set like this and evaluate this likelihood function. Because at least in some sense, if we can evaluate our likelihood function, then we can apply all the different tools we have for trying to optimize for that likelihood function. So what we'd like to be able to do is take a concrete data set like this and a proposed model, a particular graph telling us which things depend on which others, and turn that into a number, turn it into a likelihood number that we can then optimize for. So there are a few different options for doing that, and probably the simplest one that kind of illustrates some of the ways we'll go about this is to try discretizing the data, just like when we talked about back towards the beginning of the class, how we would evaluate an entropy for a stream of real value data sets. So we might, for example, declare that we can partition expression values into maybe high, medium, and low for each gene, and turn this matrix into a matrix of these high, medium, and low values. So maybe gene 1, we'll say, takes on the values high, high, medium, medium. Gene 2, low, low, medium, low. Gene 3, low, medium, low, medium. And gene 4, high, medium, high, low. So that then would give us a discretized set of data. And then we can start talking about what the values of these elements of our likelihood function would be in terms of that discretized set of data. So what we're trying to do in some sense is take the product of all of these probabilities, and in terms of computing, it's often simpler to think of this product being kind of pushed into each of these probability terms. So in other words, we would have the probability of vector A1j, product over all of the individual conditions, the probability of A2j, product over all conditions of A2j given A1j, and so forth. So in other words, what we could do is say that one component of this would correspond to the probability of vector A1 taken across the conditions, assuming that depends on none of the other variables. And if we discretize things, it's actually relatively simple to assign a number to that. What we're asking is, what is the functions are independent? We can say that's multiplied by the probability it's h, times the probability it's m, times the probability it's m. And for a particular gene A1, we can come up with maximum likelihood estimators of the probability it's h or m. A maximum likelihood estimator is just how often on average does it take a given value. So half the time we can observe it's h. So the probability it's h is 1/2, in other words. That's the best estimate of that at any rate. Likewise, here we've got a 1/2, and half the time it's n. So we've got a pair of 1/2s. And then what we end up with is 1/16. So the probability of this stream of data is 1/16. That's a likelihood, assuming it depends on none of the other data available to us. Does that make sense to everyone? All right, so things get a little trickier when we talk about a conditional probability. So the probability of A2 given A1. But we can basically apply more or less the same ideas. We're asking what is the probability that A2 is L given A1 is H, times the probability A2 is L given A1 is H, times the probability A2 is M given A1 is M, times the probability A2 is L given A1 is M. All right, so what would the probability, what would our best estimate be for the probability A2 is L given A1 is H? Well, we can observe here that A1 is H in two conditions, and in both of those conditions, A2 is L, so the conditional probability A2 is L given A1 is H is 1. Every time A1 is H, we observe that A2 is L. So you can just plug in a pair of 1s there. What is the conditional probability A2 is M given A1 is M?
1/2.
Yeah, 1/2. So A1 is M twice, and one of those two conditions, A2 is M. So we've got a 1/2. And likewise, the probability A2 is L given A1 is M is 1/2. So we can turn that into a number 1/4. The conditional probability of A2 given A1 is 1/4. That would be our best estimate at least. And we could do the same with all of the others. We would want to know the conditional probability that A3 takes on whatever values we observe, the stream of values given the values A1 takes on, and the conditional probability that A4 takes on a given stream of values given that we get to observe the values of A1 and A2. And we should be able to see how to generalize and turn each of these into a number we can evaluate. So what all of that gives us then is some way of taking the model we have and the data we have and turning that into a number. Does that make sense to everyone? Now, in principle, we could stop there and we could say that if we know how to do that, we now have a way of evaluating our likelihood function, and we just need to optimize for that likelihood function. And we could then start reasoning about how we would build and optimize it for that likelihood function. But I do want to consider some potential complications first, or some ways of improving on the simple approach I was telling you about. Very often what we want to do is actually not discretize, but really use the range of our continuous values. And that is something you can still do with these approaches. And typically the way that's done is by assuming that any of the data we get to observe is normally distributed. Very often what you'll do as a kind of pre-processing step for this kind of problem is take all of your observed values and then turn them into what are called z-scores, which basically means you center them, subtract out the average, divide them by the standard deviation, so you end up with a stream of values with mean 0 and variance 1, and then you just kind of pretend they're normal random variables. And that is often the way we'll want to solve a problem like this. We just assume that we've done this to one of our streams of values. So we can say that the probability distribution of, let's say, vector A1 is simply the thing we would get assuming A1 is normal. So it's the probability that A11 is chosen from a 0, 1 normal random variable times the probability A12 is chosen from a 0, 1 normal random variable, and so forth. And each of these is simply something we can evaluate by plugging into the Gaussian point density function. That's going to be something like 1 over square root of 2 pi e to the minus A11 over squared over 2. And we could do the same with all of the others. So we have a way of getting a likelihood for a value that doesn't depend on anything else. So we could evaluate this term here relative to that normal distribution. Now, when we start considering the conditional probabilities, things get a little messier. So we can talk about the conditional probability of the value of A2 given the value of A1. And the way we would typically do that for this kind of problem is to use what's called a Gaussian linear model. It doesn't have to be linear, but the basic idea behind it is that we assume the mean value of A2 is a function of the mean value of A1, canonically a linear function. In particular, we would assume that A2 is drawn from a uniform random variable whose mean is a linear function of A1. So it'd be some alpha 0 plus alpha 1 times A1, and then just, you can say it has variance 1. And then what we can do is learn the best fit alpha parameters to optimally explain gene 2 given gene 1. So how would we learn the best fit alpha parameters? Well, if we wanted to find the best way of explaining gene 2 as a linear function of gene 1, how would you do that? We saw this back when we looked at linear algebra. So this would be an example of a linear regression problem. And what we could do is say that we observe some set of values for gene 1 and gene 2. We could pose a matrix where we're trying to solve for alpha 1 and alpha 0 here. We would say we've got a set of 1s everywhere, we've got an alpha 0. We've got a set of whatever values we have for gene 1. And then if we had a perfect fit, those would give us back exactly the values of gene 2 in the same conditions. And if we don't have a perfect fit, we do least squares regression, solve the least squares best fit alpha 1 and alpha 0 parameters. And then we know the best linear model to explain A2 in terms of A1. And then we just assume that our likelihood values are the noise that's left over from the values of A2 beyond what's present in this model in terms of A1. So in other words, we could say that this is the probability of, say, value A21 given value A11 times the probability of A22 given A12, etc. And that's going to be given by the product over all of these Gaussians. So 1 over square root of 2 pi times the probability of generating A21 from A11, assuming that there's a linear relationship there. That's going to be e to the minus the measured value of A2 minus the predicted value from the regression model, which is alpha 0 plus alpha 1, A11. So that is your error in a sense. Square that divided by 2 to get a Gaussian term, and then repeat that for each of the other components. So e to the minus A22 minus alpha 0 plus alpha 1, A12 squared over 2, etc., repeated across all of the observed conditions. So that gives us a way of specifying a conditional likelihood for gene 2, assuming it depends on gene 1. That's, as I say, the most common way of doing this is to assume something like the linear regression model for the mean value of gene 2 and then assume Gaussian noise around it, which gives you a way of turning the deviation from that mean into a likelihood function. So does that make sense to everyone? Okay, so what all of this is getting at is basically a way of specifying what our likelihood function is. So in some sense, we've now gotten to the point where we can talk about the probability of our observed data set given a particular graph model. And we now know how to evaluate that. So we have a routine, at least, an algorithm we could apply or write a computer program to apply that turns that into a number. Very often, we would also want to throw in, as I mentioned, a prior probability. So what might be a good prior probability over graphs? Well, we saw a couple of examples last time of typical anti-complexity priors we could use. So this could be a BIC score or an AIC, so different ways of penalizing for complexity of the graph. If we wanted a BIC, then this prior probability would be something like e to the minus number of edges in G, call that e sub G. That would be an example of a prior probability we could use that would bias it towards simple graphs. But one way or another, we're going to get a likelihood function where we can talk about the probability of our data given our model, and then maybe a prior on the models. And then what we want to do is use that to find the actual network model. So how could we do that? Well, suppose we wanted to pose this as an optimization problem. What's a technique we could use to do that? To try to maximize the likelihood over graphs? Well, it's probably going to be an intractable problem. So generally, it's messy enough, you probably won't be able to come up with a good approximation algorithm, but we can apply any of the sorts of heuristics we've seen. So genetic algorithm, or hill climbing, or simulated annealing, whatever. So all of those would give us ways where once we've got a candidate graph, once some starting point, we can evaluate this for any particular graph. We can try perturbations, adding or removing edges, see if they improve the quality of the likelihood or make it worse. Once you know how to evaluate this, it's pretty easy to then start considering any sort of heuristic optimization we want to do. What if we wanted to pose this as a sampling problem and generate a sampler over possible graphs? What might we do there? Let's say we wanted to make a metropolis sampler for the posterior of this likelihood function. Well, our state space here would be the set of graphs. So we could say that we start with some initial graph. Let's call it G. So maybe we've got a graph we're considering here. And then we would want to pose a set of candidate moves. An obvious one would be to say that our possible moves are taking any edge either in the graph or not in the graph and flipping whether or not it's in the graph. So we might pick this edge, and then our candidate next graph would be missing that edge. Or we might pick an edge that isn't there, and our candidate next graph would be a graph that adds that missing edge. So basically just turn it into possible moves, being flipping the presence or absence of one edge. And then it would be relatively easy to take a model like this, a likelihood function, evaluate that for G and G prime. So we can talk about probability of the data given G, probability of G, and we could evaluate the probability of the data given G prime times the probability of G prime. And in fact, these are typically a lot easier than going back and reevaluating this whole thing again, because if we've only changed one edge in the graph, really all we need to do is see what that edge is pointing at. So maybe if we remove this one, you see that that's pointing to this node. You really just need to reevaluate the probability of the expression vector corresponding to that node, because none of the others have changed. So you've got a relatively small amount of work to compute what changes between this and this, and likewise, typically a small amount has changed between the computation of the priors. So we can get these particular values, and then what would we do with that? How do we use these to build a sampler? Well, if we're trying to do metropolis sampling, typically what we would want to do is we'd do that evaluation, maybe we fit our regression models, we get these two particular values, and then what we're really considering is the ratio of those values. So with metropolis, you're always looking at ratios of likelihoods between the two endpoints of the model edge you're considering. Since we're looking at the ratio, basically everything averages out except the component of the model that relates to how we're explaining the likelihood of that particular vector and what we've changed in the prior computation. So usually a small amount of work will give you this ratio. And then let's say we call this R. Can anyone tell me what how we implement a metropolis stack using R? Under what conditions do we take the move from G to G prime?
If R is greater than 1?
Yes, if R is greater than 1, we always take it. If R is less than 1, then that's the probability of taking it. So that basically gives us a metropolis sampler over this likelihood function. And once you've got that, you can run through possible graphs. And it might take a while, but at least in some sense, we have a way of building something that will give us a reasonable sample over the universe of possible graphs and give us an idea which edges are we really confident should be there, which maybe have high uncertainty, which are we confident shouldn't be there. And that more or less is how we would be able to work with this kind of problem in practice. So does that make sense to everyone? And so there are a lot of complications in the real world when people work with these kinds of problems. So things are worth knowing about. We might have other information we can use to help build this graph. So maybe we've looked in a database and it's told us that some of these edges should be there and some edges shouldn't be there. That stuff we can pretty easily build into our prior model. So maybe we've got an anti-complexity prior, but we can also say if we think this edge is really likely to be there because lots of databases say it's there, then we can add in a prior where if the edge is there, you give it a nice bonus. If the edge isn't there, you give it a penalty. So that kind of thing. These Bayesian models tend to very easily incorporate prior information. So usually if you have any, you want to use that. They also make it relatively easy to incorporate other sorts of data. So maybe we've got expression data, but we also have binding data. So we have data that tells us maybe that the experimental evidence looks like this gene binds to the promoter of this gene. That also is something you can incorporate into these models by simply saying that our likelihood function is the probability of our expression data given G times the probability of our binding data given G. So if you treat these as two independent outputs of the same physical system or the same model, then you can just multiply them in Bayesian models. They'll do the right thing. And then if you have a way of evaluating this, so the problem's about as easy as it is with just the expression data. That's one of the reasons those models are very popular. They're very good at dealing with heterogeneous data sets of different kinds of data that you bring into the same inference. So any questions about that? All right, so we're running out of time here. There is some additional stuff that's in the text where I talk about moving to even more complicated kinetic models where you consider effectively differential equation models of how these genes influence one another. That's an even harder problem, and people have to be more aggressive about pruning the models, throwing out edges that probably aren't there, and looking at smaller data sets. But basically, you can bring in other sorts of ideas we've seen in this class there. But I hope that gives you a feel for how some of the many techniques we've covered, especially in this last half of the class, or last third of the class, fit into this particular problem area. And this, I think, is a good representative of a lot of problems in kind of systems biology, the examination of large, complicated biological data sets. So any questions about any of that? Okay, then I guess we'll stop here. As I mentioned, I do have some homeworks to hand back to you guys.